Hello and welcome to this AMETEK Land webinar. My name is Katie and I will be your IEEE Global Spec moderator. Now I would like to introduce today's presenter, Manfred Hayk. Manfred is the Global Infrared Product Manager at AMETEK Land. With a degree in physical engineering, specializing in laser technology and optical metrology, Manfred has over 20 years of technical, product, and application development and sales support experience in optical and infrared metrologies. He focuses on developing AMETEK Land's full range of non-contact temperature measurement products, including process thermal imagers. Manfred, welcome to today's event. And with that, I'd like to pass things along to you to get you started. Manfred, go right ahead.
Welcome to the AMETEK Land webinar discussing the advantages in non-contact temperature measurement in metal reheat furnaces. My name is Manfred Hayk. I'm the Global Product Manager for AMETEK Land Infrared Products. During this webinar, AMETEK Land introduces how advantages in accurate non-contact temperature measurements in metal reheat furnaces ensure optimum product quality, reduce wastage, increase energy savings and consistent metallurgical properties, and minimal surface scaling. It considers the requirements and challenges for infrared temperature measurement in reheat furnaces for bringing cold metal to the correct temperature for rolling, extruding, or forging. Let's start with some fundamentals of non-contact temperature measurement and its use in metal reheat furnaces. Most rolling and forging plants use reheat furnaces to reheat their stock to a uniform temperature according to the further process, following a tightly controlled heating curve. While different furnace designs are present in the industry, like beam or batch furnaces and walking beam furnaces, walking beam furnaces provide a much more uniform underside temperature than other designs, which results in higher quality finished products. Mainly used heating methods are natural or methane gas and natural gas with oxygen enrichment, which is more efficient. Regardless of the furnace design or fuels used, it is very important to accurately measure the temperature of the stock and its progress through the furnace. The main challenge of measuring accurate stock temperatures in reheat furnaces is the interaction of the direct emission of the object, which temperature should be measured, and the mostly hotter background temperatures of the reheat furnaces. To understand these challenges in more detail, I will go through some basics of infrared non-contact temperature measurement first. The object emission, or spectral emission, is the main parameter for accurate temperature measurement of the stock temperature. While each object is emitting a certain amount of mainly infrared radiation based on its own temperature, the emissivity is defined as the ratio of the emitted radiation of a real object to the emitted radiation of a black body at the same temperature. The emission, usually given in percentages between 0 and 100%, is the specific spectral emission of each object, depending from its material, surface, viewing angle, and its temperature. In these applications, steel and metal surfaces mainly have emissions bigger than 60%. Gustav Robert Kirchhoff shows that the sum of all radiation at each time is absorption plus reflection plus transmission of radiation. Further, Kirchhoff shows that the absorption of a material or surface is the same like its emission. This results in an important basic physical law for non-contact temperature measurement. The sum of emission, reflection, and transmission is 100% or 1. In our case, metals usually do not transmit any infrared radiation, so the transmission is zero. For these kind of materials and surfaces, 1 or 100% is each time emission plus reflection. The emissivity is the main parameter which describes the amount of emitted radiation of an object with regards to the material, surface, viewing angle, and of course its temperature. Another important fact is that the intensity of heat radiation and infrared radiation increases with its temperature at the force power, detected by Stefan Boltzmann. It means if a cool object is running into a hot furnace, the hotter furnace walls and parts will reflect on the object surface by its reflection factor. The lower the emission of the stock surface is, the higher is the reflection influence from the background. And if the furnace temperature, refractory temperature for example, is 2 times bigger than the object temperature, the intensity of the hotter background radiation is 16 times bigger than the radiation emitted by the object or stock in the furnace, multiplied by its emissivity. It can be a huge influence we need to care for while measuring accurate stock temperatures in reheat furnaces. Let's take a look to a short example. If an object in a furnace has a temperature of 100 degrees C and the furnace refractory has 1000 degrees C and the object emissivity is 70%, a pyrometer or a thermometer would measure the complete radiation signal of the object radiation power multiplied by the object emissivity plus the refractory background radiation power multiplied by the reflection of 30% of the object surface multiplied by factor 10,000 because of the higher background temperature. So this can be an essential influence to the temperature reading of the stock in the furnace. This is why we need to compensate for the reflected background radiation to enable an accurate object temperature reading. Based on the described behavior, it is essential to use an appropriate measuring system to achieve most accurate stock temperature measurements, which can be fed back to the furnace and process control system. As each system reads the sum of the direct emitted and the reflected radiation on the object surface, it is necessary to consider and measure the background temperature and subtract it from the signal readings. To measure these background temperatures, it can be done by using the thermal imaging system itself, which is usually measuring the furnace refractory too, or an additional pyrometer measuring the background refractory temperature, or an existing thermocouple feeding these temperatures back into the measuring system for accurate compensation. Another important influence to the temperature measurements in reheat furnaces is the fuel which is used. If a furnace is fueled with clean methane natural gas, usually a 1 micron thermal imaging system is used, while a 3.9 micron system is also unaffected by the products of combustion, hot combustion gases. If dirty fuels are used, they produce significantly more CO2 and water. At 1 micron, there may be interferences from those combustion products. See the comparing thermal images at the bottom of the slide, which shows the same scene taken with a 1 micron and taken with a 3.9 micron thermal imaging system. A well-documented atmospheric window exists in a narrow waveband around 3.9 micron, in which the hot CO2 and water don't emit. So an instrument operating at 3.9 micron is unaffected by this atmosphere to provide a clean image and accurate stock temperature readings. What are the traditional and next generation sensors available for accurate reheat furnace temperature measurements? Commonly used thermocouples are installed in most furnace types, and the furnace temperature zones are usually controlled by the temperature readings. Based on calculated models, the temperature of the stock is then determined, while the thermocouples are installed penetrating through the furnace refractory wall, measuring near to the internal refractory surface. These measurements are of course indirect. It means they measure the furnace gas temperatures, but not the direct object or stock surface temperatures. These needs to be calculated based on those model calculations. And such thermocouples may have a drift and need to be exchanged over the time. The main advantage of non-contact temperature measurement is that this method allows to measure the direct object surface temperatures. It's typically done by infrared pyrometers, measuring spot temperatures, or thermal imaging systems, measuring whole thermal images with thousands of measuring points or pixels. By choosing the right spectral response, the non-contact temperature measurement is independent from possible influences of hot combustion atmospheres. Advanced thermal imaging systems provide much more details of the stock and the furnace temperatures, the temperature deviation, and additionally provide an online view into the reheat furnaces to the operators 24/7. With the near-B measuring at 1 micron and the FTI-EB measuring at 3.95 micron, two industry-proven systems are continuously working in many reheat furnace applications around the world. Different field of views provide different wide-angle optics to get the optimum view and measurements related to the specific furnace and the camera position, working at measurement temperatures up to 1600 degrees or 2912 Fahrenheit. The near-B and the FTI-EB thermal imaging systems provide an accurate and reliable real-time process control, including automatic file archiving and storage of temperature data based on the advanced thermal imaging software LIBS. This system supports quality control, enables continuous process improvements, increases the process and product quality and the process efficiency, and finally decreases emissions. So, what's the importance of continuous thermal imaging temperature measurement of the entire metal stock? Reheat furnaces bring cold metals to the correct temperature for rolling, forging, and extruding. The temperature should be very uniform throughout the product, which requires accurate temperature monitoring and controlling. Temperature measurements are also key to provide optimized heating curves. This results in energy savings, consistent metallurgical properties, and minimal surface scaling. For maximum fuel efficiency, stock should achieve desired temperatures shortly before discharge. If the stock is heated too quickly, energy is wasted and cost increase, and the properties and the surface of the stock can be affected. Heating need to be uniform to ensure the entire product is at the correct temperature, for example in forging processes, to prevent damaging of the forging tool and negatively affect the forging and product quality. As discussed previously, traditionally thermocouples were installed to control the different temperature zones in the furnace. While the thermocouples do not measure the exact stock temperature but the furnace atmosphere and surroundings, pyrometers and thermal imaging systems allow most accurate temperature reading of the stock. As quality requirements continue to increase, more companies are switching to process pyrometers and thermal imaging systems on a global base. These systems provide a high-quality image and are fully radiometric, enabling accurate temperature measurements within the scene while automatically compensating the background radiation. While pyrometers delivers just one measuring point, thermal imaging systems provide measurement points, areas of interest, and profiles within a live image of the process 24/7. A great advantage to the process control, quality, and efficiency. These application-specific pyrometers and thermal imaging systems need to use advanced spectral filtering to be unaffected by different fuels and the resulting hot combustion gases. Especially with higher background temperatures of the furnace refractories, the background radiation influence needs to be continuously measured and accurately subtracted from the measuring signal. The reheating process needs to be closely controlled and monitored to ensure the metallurgical properties of the stock reheated homogeneously. A clear visible image of the stock reheated in the furnace needs to be provided to the furnace operator. These systems need to be reliable for 24/7 operation in rough industrial environments at high furnace and surrounding temperatures. What are the AMETEK lens solutions for highly accurate non-contact infrared temperature measurements in reheat furnaces? Many customers using portable pyrometers, like the proven lens Cyclops C100L or the C390L, providing correct spectral responses to the used fuels in the reheat furnaces. A very clear reel-through lens sighting allows the most exact alignment of the measuring spot, while the instrument is built for rough environmental industrial conditions and handling. These portable devices are used for sporadic measurements and with possible access to the heated stock in the furnace. It is recommended to take these manual measurements from the top surface of the stock right at the opened furnace door to avoid background reflections and influences. A possible background temperature can be taken into account via the Cyclops logger software to correct the reading if necessary too. Up to 10,000 values can be stored in the instrument and monitored with the Cyclops logger software for further analysis. The LAND FTS is a reliable furnace temperature measuring system based on spot pyrometers. Providing advanced spectral filtering, these pyrometers avoid any effects of hot combustion gases like CO2 or water. With the spot thermometer secondary input, a background temperature can be directly fed back to the instrument for continuously background compensation. The background temperature can be taken by an additional background spot pyrometer, measuring the refractory temperature. See picture at the upper right side of the slide. Or using an existing thermocouple mounted in the direct reflection angle range to the stock surface. Given this system configuration, the object pyrometer measures the stock surface temperature, providing accurate true load temperature by subtracting the background reflection influence online 24/7. One main benefit of thermal imaging systems is, while pyrometers measure a single point, thermal images measure the temperature deviation accurately across the whole image from any of more than 300,000 or even more data points. A particular advantage of thermal imaging is the live visual image. Operators can identify potential problems, for example hooked billets, and possible surface property issues while measuring the temperatures at the same time. Traditional thermal images require large holes in the furnace wall or a big flange with a protection window, leading to costly heat weightages and heat damage to the camera, or even viewports are required to be cleaned and maintained. The near-B and FTIEB borescope optics needs just a small hole in the refractory and are installed sealed to the process for 24/7 operation. No hot furnace gases can get out of the furnace and the system is easily accessible too. While these thermal imaging systems delivers high-resolution thermal images, the advanced software package gives exceptionally detailed monitoring and control over the thermal imaging measurements in reheat furnace processes. It provides extensive control and analytical functions for exceptional process control, including AOEs, areas of interest, point or area temperature measurements, temperature profiles, histograms, isotherms, measurement trendings, which can be captured continuously or in case of an event, for example, abnormal process temperatures, enables data exchange using a simple cross-platform TCP/IP protocol, optional OPC server, or analog signals or alarm outputs. The powerful image processing allows for real-time analysis of the thermal imaging information provided by up to 8 images running at full frame rate. An existing system can be extended easily at any time too. It's all about quality control, cost savings, and efficiency increasing. Achieving all of these main goals, accurate temperature measurement and thermal imaging, is supporting to even overachieve these goals and have an essential quality and market benefit, which is traceable. What are the main benefits? Accurate temperature measurement and optimum process controlling saves energy and reduces fuel costs. Process efficiency optimization by increasing the throughput and reducing downtime periods. Improving production yields and furnace life by reducing furnace temperatures. Protecting downstream processing machinery from under-temperature products. Dust-free optical systems consuming minimal instrument air. Product and furnace temperature trending and capturing. What are the main benefits? Accurate temperature measurement and optimum process controlling saves energy and reduces fuel costs. Process efficiency optimization by increasing the throughput and reducing downtime periods. Improving product yields and furnace life by reducing furnace temperatures. Protecting downstream process machinery from under-temperature products. Product and furnace temperature trending and capturing. And dust-free optical systems consuming minimal instrument air. Thank you for your interest and participation so far. During this webinar, we already received first questions I would like to answer in addition to your upcoming questions.
Manfred, thank you so much for that great presentation. As you mentioned, we do have some questions that have come in from the attendees. Here is our first question. This question is from Paul. What about the influence of the viewing angle of the pyrometer or thermal imager to the object with regards to the temperature reading?
Thank you, Paul, for this interesting question. You are right. The temperature reading depends from the viewing angle with which the pyrometer or the thermal imager is aligned to the object to be measured. Within a viewing angle of plus minus 45 degrees perpendicular to the object surface to be measured, there is no effect to the temperature reading. Bigger viewing angle would cause a decrease in emissivity and changing temperature reading. Usually, the pyrometers and thermal imagers used in these processes are installed from the side wall of the reheat furnaces and observing the side face of the stock. This is the temperature and temperature deviation which can be measured accurately. The optimal measuring position can be determined during a site visit from one of our global engineers and based on furnace drawings, dimensions, and related zones.
Okay, Michael now asks, What happens if there is a coolant failure, cooling water or purging air?
Well, basically, if the cooling water and/or the purging air fails, there is an alarm signal integrated in the system, provided to the operator team on site. If the time solving these issues get too long, it can happen that the camera system is overheated and can get damaged. That's why AMETEK Land provides auto retraction systems, which automatically retract the whole camera system in case of a cooling water and purging air failure, and if the tip of the borescope lens gets too hot. These systems automatically retracts the camera to a safe position, where it is easy to access even if all power, water, etc. fails. So the system is safe.
All right, great. Thanks, Manfred. Here is a question from Mario. If the temperature difference of the stock and furnace is very high, he uses an example of start of the warm-up process. What about the accuracy of the measurement?
It's a good question, Mario. As discussed during this webinar, the higher the background temperature of the furnace in comparison to the object temperature is, the higher is the influence of the background radiation to the temperature reading of the object. Usually, really cold objects are inserted to the process to be homogeneously reheated to the desired process temperature. At this stage, it is important to see these cold objects, and it will take time to reheat them to the process temperature. The most accurate temperature reading needs to be done during the final heating stage, where the absolute temperature and the homogeneous temperature distribution is important for the further processing steps like rolling or forging. During these steps, the temperature differences between the furnace background and the product temperature is much smaller and can be measured accurately, considering the actual background temperature.
All right, here's another question. Is it possible to capture the background temperature directly with the thermal imaging system without using an additional pyrometer or thermocouple?
A simple answer, yes, it's possible. As discussed, you can set AOEs, areas of interest, and if you set an area of interest pointed to the furnace refractory, you can use this temperature reading at an emissivity setting of 100% for the background temperature. This reading will include all multiple background reflections to one value. The software then allows to input and calculate this temperature reading as background temperature. Using the spot parameters, you can use the secondary input to input the background temperature reading from an additional parameter or thermocouple. The background radiation is then corrected in the spot parameter itself, giving the right object reading temperature.
Okay, Manfred. Frank has 2 questions. Can the thermal imaging software also be used remotely? And is the PYROMETER software available too?
For both of your questions, Frank, yes. You can use the thermal imaging software remotely as a server and optional client version installed in the company network. For longer distances to the camera position, we usually use fiber data connections working reliable in industrial environments. And yes, the very new Spot Pro software package is available for download from our webpage and to have a 30-day trial. It allows the full access, monitoring and data capturing for any spot parameters.
All right, Manfred, we have time for one more question. This one is from Michelle. Is it possible to recognize a product or its position using the thermal imaging system?
This is an interesting question for Michelle too. Thank you for this. As we discussed, in these applications, the thermal imaging systems usually sees the product and the background which has a higher background temperature. Especially if the temperature differences are lower, the temperature contrast isn't possibly as high as expected. In this case, it would be possible, for example, to integrate a water-cooled tube in the furnace and in the background of the object to be measured. Using desired ROEs, areas of interest, in the thermal imaging software, it is possible to detect the size and the orientation of the product in the furnace too. Of course, it depends on your application and should be discussed during a site visit.
All right, Manfred, that's all the questions we have for today. We are going to wrap things up right here. Manfred Hayk, I want to thank you so much for taking some time to be here with all of us today. And thank you to all of our audience members for being part of this webinar event. Manfred, I'll pass it back to you if there's anything else you'd like to say.
Thank you for your attention and interest to this webinar discussing the advantages in non-contact temperature measurement in metal reheat furnaces. We are really looking forward to receiving your further questions by email to lend.inquiry@ametek.com or manfred.hayk@ametek.com. Additionally, you are kindly invited to visit our webpage for further informations. Thank you very much and goodbye.
All right, thank you so much, Manfred. Again, thank you all for taking time to attend this webinar event. Take care, and we'll talk with you soon.